Hi guys, so today we're going to be doing lesson 2.7, Exploring Intermolecular Forces. Our objectives today are to create and or evaluate models that illustrate how molecular properties are influenced by the types of intermolecular forces present in a substance, and also to create and or evaluate a claim about the types, strengths, and origins of intermolecular forces present in a substance. So we're going to start today with part 1, exploring boiling points and evaporation rates. So let's recall heating curves. I want you to describe what's happening at each phase or state or position in the graph. All right, so we're going to start with A to B, B to C, C to D, D to E, and E to F. Now I want you to find your handout 2.7a. Just take a moment to examine the table and the graph provided. As you can see, you've got 4 substances. Methane has 1 carbon, ethane has 2 carbons, propane has 3 carbons, and butane has 4 carbons, and their boiling points are graphed next to them. I've also provided an image of those 4 molecules below. What do you notice about their size? Okay, so what we're going to do is a quick activity to determine which alcohol evaporates fastest. So how is evaporation different from boiling? How is evaporation similar to boiling? Why can't we use the alkanes in the data table for our experiment? So the reason is that alkanes are all gases. And so alcohols are very similar to alkanes, but they are liquids, and so we can watch them evaporate easier. Why can we smell the alcohols when the bottles are open? What's happening at the particle level? So think about the diffusion of a gas. Though we did this in Unit 1, virtually that was really hard to do, to smell the essential oil. But just think about how a smell protrudes through your house, and think about what those particles are doing, okay? And so here's just a quick look how alcohols are close to alkanes. So butane has this hydrogen at the end. There's nothing but carbons and hydrogens. Butanol, which is the alcohol, has an OH at the end, and that's the only difference. Okay, so those are going to be very similar to what you're going to see in the video next.
Evaporate some alcohols. I have my stopwatch here, but I don't think I'll be able to do this and show that to you at the same time. So I'm just going to tell you the evaporation time, and then it's a very simple lab. We're going to dip a cotton swab in one of these alcohols, and I'm going to wipe it on the desk. I'm hoping that you can see that happen, and then recording how long it takes to evaporate. So we're going to start with N-butyl alcohol. So this is butanol. I'm going to dip that cotton swab and wipe it and hit start. I'm going to hit lap so I can do this a little bit faster. The other one is going to be isopropyl alcohol. It says propanol on your thing, but we're going to use isopropyl instead. Wipe it and start that one. This you can get at any store, like Walmart, except during COVID, because apparently they want to use all that up. And the last one we're going to do is ethyl alcohol, or ethanol. This is harder. It's wider mouth. And we'll start that ethanol time. I put too much. I soaked my cotton swab for the isopropyl, maybe a little too much. It'll be okay. Where I had too much isopropyl, you can actually watch it evaporate pretty quickly right there. So our butanol is now gone, and our isopropyl is now gone as well. So for those times that you'll need to record, let's do some math. So overall, the butanol took 4 minutes and 32 seconds. That was the easy one because that's what my timer just says there. As far as the propanol, we need to subtract 28 seconds from that, so 32 minus 28 is 4. So the propanol took 4 minutes and 4 seconds. So the isopropanol took 4 minutes and 4 seconds. And then the one I really need to calculate is the ethyl alcohol. It only took 44 seconds to evaporate the ethanol.
So after watching the video, were your predictions correct? Why or why not? What were you thinking? So the next thing we're going to look at is the relationship between molecular structure and boiling and evaporation rates. So here we've got different structures, right? We've got methane, nitrogen monoxide, and ammonia, and their boiling points are listed next to them. What do you notice about the molecules in this data table compared to those that we looked at earlier? Are these data consistent with explanations about the boiling point and evaporation rates of a substance? So next you're going to watch a video about a gecko climbing a wall. We're going to talk about how this also relates to intermolecular forces. Now, after you watch that video, how are the geckos able to climb walls, right? So the video is going to lead into the article about intermolecular forces and the structure of those gecko feet. While you're reading that article, what are the forces that allow geckos to stick to walls? Why do they occur? Can you think of a substance maybe that the gecko can't stick to? And how is the phenomenon of geckos' feet sticking to a wall similar to the behavior of molecules in a liquid state, that evaporation rate that we just looked at? All right, now, after you've read that article, we're going to spend some time just taking some notes on intermolecular forces. This is on handout 2.7b, C. You can see the notes. It's a table of notes. So we're going to start with talking about London dispersion forces, which are the ones that we read about in the article. A London dispersion force occurs from the just random motion of electrons. And then as those electrons are moving, sometimes if there's two electrons, they're on the same side as they're rotating around the nucleus of an atom. That's called an instantaneous dipole. Okay, so an instantaneous uneven distribution of electron creates a dipole on one side of the atom versus the other. Well, if there's a slight positive charge, that's going to attract negative charge to it, and you end up with an induced dipole in a neighboring atom. Okay, so this is just helium, as it has two electrons. They happen to be on the same side. That creates an instantaneous dipole that then induces other dipoles. However, because it's due to just the random motion of those electrons, they are not very strong and they don't last very long. Okay? So these are very, very weak. They're the weakest of all of our intermolecular forces. They're caused by the motion of electrons. Think of the Pirates of the Caribbean. Remember in, I don't know which one, Pirates of the Caribbean 40. Jack Sparrow had to flip the boat over and they ran back and forth. So think about the more people he had running back and forth across the ship, they got the ship to flip over. The more electrons you have orbiting around the nucleus, the more pull you're going to have as that random motion occurs. So London dispersion forces increase as the number of electrons increase. This does not make them have relatively high melting or boiling points because it is a weak intermolecular force. And in general, this does not increase water solubility. Our next force is called a dipole-dipole force. We've talked about dipoles, right? Dipoles occur when we have a polar bond. So a polar molecule is also known as a dipole. Well, polar bonds near each other will also create an intermolecular force between those attractions, as you can see here between the HCl molecules. Because that chlorine is partially negative, it attracts the partially positive hydrogen from a neighboring molecule. That electrostatic interaction between those oppositely charged regions is called a dipole-dipole force. This will somewhat increase their melting and boiling points, and in general, increases the substance's water solubility. It will dissolve in water. So next what we're going to do is we're going to look at this PhET simulation on molecular polarity. Here's an image of it a little bit, but we're going to watch it happen here. So if I just have two atoms, right, and I have that atom B is more electronegative, right? So I made a bigger bond dipole. You can see the partial charges here, but it always points towards the more electronegative atom. Okay. And if I turn an electric field on, if I try to move that molecule, it will always end up having this orientation because the partially negative side of that B atom is attracted to that positive electric field. Okay. Our third intermolecular force is called hydrogen bonding, and you may have heard about this when you were in honors biology last year. If you weren't, that's okay. We're going to talk about it now. So hydrogen bonding is the attraction between a hydrogen atom of a molecule to an unshared pair of electrons in another molecule. Hydrogen bonding occurs in molecules where hydrogen is covalently bonded to a very electronegative atom. And in fact, this will only happen when hydrogen is bonded to N, nitrogen, O, oxygen, or F, fluorine, NOF. So hydrogen bonding only occurs when hydrogen is directly bonded to N, O, or F. This is our strongest of all intermolecular forces. Hydrogen bonds are possible because hydrogen atoms only have one energy ring. So when they make that bond with just those two electrons in its outer shell, and you have a highly electronegative atom that pulls it away, that actually creates, there's less shielding of the nucleus with other electrons, and you actually expose the nucleus, which makes that hydrogen even more positive than a different atom would have. Hydrogen bonds are responsible for a lot of physical properties of many biological substances. It's how your DNA unzips and replicates. It's how water has its polarity. And so water has hydrogen bonds between it. That allows water to have a high surface tension. It allows water to have a high specific heat capacity. It allows water to have capillary action so that trees can grow. Really, the whole basis of life comes from these hydrogen bonding interactions. Now, I hate that they're named hydrogen bonding. They are not bonds. These are intermolecular forces. They're forces between the particles, okay? So what are two main factors that determine the boiling point of a substance? Think about our first evaporation rate, and let's go back and look at these, right? What do you notice about these? They're all about the same size, but we have a very different boiling point. Now that you've heard about intermolecular forces, what relationship here allows these molecules to have such different boiling points? What's the relationship between size of molecules and their boiling points? And why is hydrogen bonding the strongest type of intermolecular force? I want you to be able to explain how boiling point relates to the strength of the intermolecular forces in a liquid. So thinking about those alcohols. As you've been answering your questions, here's the graph for question 4 through 6, right? And there's things that you need to notice about these molecules, right? Not only does size play a factor, what period number they are in, but also look at who they're bonded to, N, O, and F, right? And so having those hydrogen bonding interactions, all of these are bonded with hydrogen, but how that affects the boiling point of a substance, okay? So in part 3, I'm going to put you in your breakout rooms and you're going to fill out the first 3 in your table using the link to the Concord Lab. And our enduring understanding, the macroscopic physical properties of materials can be explained by the intermolecular forces among the particles. The fact that evaporation rates are affected by the size of the alcohol. The fact that polarity and hydrogen bonding affect the evaporation rate or the boiling point of a liquid or a gas, or even really a solid. The structure and properties of compounds that arise from physical properties and bonding patterns of the constituent atoms, right? So we know that properties arise from these structures, and that is all due to those valence shell electron pair repulsion that allows to have those dipoles not canceling, which gives us dipole-dipole interactions as well as hydrogen bonding interactions.